and welcome back. Over the past several videos, we've been focusing on differentiation and limits, and their applications to several different types of problems. For example, optimization, related rates, root finding algorithms, and also calculus and analysis of change in parametric and polar coordinates. As mentioned at the beginning of this series, calculus is a lot more than limits and derivatives. There are several other problems that also need to be understood in order to appreciate all of the wonders and beauty that calculus can provide. And one of the other methods and tools or problems that I introduced in the beginning was area accumulation. So let's recall some of the basic ideas that we discussed in the very beginning in terms of area. So what we're going to do is we're going to be analyzing some function on some interval. And let's assume that that interval is the interval a to b, where a and b, let's assume, are finite, at least for now. For this picture, I've just drawn a function that appears to be continuous, but generally speaking, we're going to consider the discontinuous cases at a later time on how area underneath it may be affected. So what we're going to be doing is we're going to be targeting how to find the area underneath this curve on this particular finite or potentially infinite interval for this particular function f. So what is this area equal to? Before, we didn't really give it any special notation, but now we will. So I'm going to represent this notation using this symbol, which is called an integral. And since the interval changes the area under this curve, then assigning some notation for the interval on that integral should be necessary. The lower bound on the integral will be the lower bound of the interval, and the upper bound of the integral will be the upper bound of the interval. Obviously, the function that we're finding the area underneath also needs to be represented or mentioned. Therefore, we're going to be naming that function f underneath that integral sign. And we're also going to be putting this little symbol dx at the very end. More on why we're motivated to put that little dx at the end a little bit later. And again, this notation can be read as just the integral. So the integral, some people will also say the definite integral of f from x is equal to a to x is equal to b. So let's firmly state the questions that we're aiming to solve now. Question 1. How to find a exactly. How to find the value of integrals precisely. Now, can we always do this? Not really. So we cannot always do this, at least not in a practical manner, right? So that's kind of sad, at least to some degree. Question 2, if we can't find the area exactly, can we always approximate it? If so, how to approximate it? So if we can't find it exactly, can we always approximate it up to some certain degree? And the answer is, can we always approximate it? Yes. And we also have many ways of doing so. Some better than others. That's what our focus will be today. So, when we originally introduced this problem of finding or approximating areas under curves, we presented two ways of doing so. The first of those ways was via something called left-endpoint rectangles. So left-endpoint rectangles. So let's just draw a little picture to remind us how that exactly worked. So we have some function f on some interval ab. Let's assume this is a and this is b. And let's assume that we partition this interval into 4 subpieces, each of which has the same exact length. And let's call that length delta x. So delta x for each of them. Theoretically, can you choose those lengths to be different? The answer is yes, but we're going to keep them all the same, just for simplicity purposes only. So what we're going to do for each of these intervals is we're going to project from the left endpoint for each of those intervals. When we do that, we're going to project that point up to the curve, and once we hit it, we're going to have a rectangle on that interval of that height. So at this point, we're going to have a height at that point. At this point, we're going to have an interval up to that. Here, we're going to have this rectangle here, Let's pretend all those rectangles are the same length, of course. So when we find the areas of those rectangles, and the area formula for a rectangle is pretty easy, we're going to have some approximation to the area under that curve. Notice, for example, this one on the left is an under approximation, where the one on the right is an over approximation. Usually for left endpoint rectangles, if you have a function that is increasing, usually left endpoint rectangles are going to be an under approximation, and if the function is decreasing on that subinterval, left-hand rectangles are typically going to be an over approximation. And when it sort of switches in between increasing and decreasing, the total amount hopefully balances out. So, how do you find delta x for a general interval AB, where you assume that m is the total number of subintervals that you want? So if n is the number of subintervals, delta x can easily be found by taking this total length b minus a and chopping it up into n equally divided lengths. So once we have that, how are we going to find these areas? So the area for this particular first rectangle is dictated by the point A. This x value is a plus delta x. This next x value is a plus 2 delta x. And this value here is a plus 3 delta x. Notice that the very first point can also be represented as x is equal to a plus 0 delta x. The reason I write it like this is because keep in mind n is equal to 4, and we're going from 0, 1, 2, up to 3, and that's the last height value that we're going to be interested in. So if we write this in expanded notation to try and get a formula for it, this area obviously depends on how many rectangles we're going to have, which I'm going to represent by m, and these are all left endpoint rectangles. So the approximation generated by n left endpoint rectangles I will denote as a and l. So the height of all of them are going to be delta x, and keep in mind the area of a rectangle is just equal to length times height. The length for all of them are the same, so I'm going to factor out the length out of each of those formulas. So I'm going to have delta x in the front. So I'm going to have delta x times the sum of each of their heights. The first height being f of a, the second height being f of a plus delta x, the next height being a plus 2 delta x, and this is going to continue all the way down to f of a plus m minus 1 delta x. Again, why m minus 1? You can sort of see from this particular pattern that 3 is 1 less of 4, and regardless of the value of n, that's always going to be the pattern. So if we want to express this in summation notation, which will allow us to code this in languages such as MATLAB or Desmos, what are we going to have? So a and l will be equal to delta x multiplied by the sum from some index that ranges from 0 to m minus 1 of f of a plus k delta x. And that is the closed formula for left endpoint rectangle approximations for areas under curves. Let's do an example. Suppose we have the function f of x is equal to e to the power of minus 1/2 x squared. I highly recommend you try and find the derivative of this, because this is going to tell you whether it's increasing or decreasing on some subinterval of interest. So let's assume that we desire to find the area underneath the curve from x is equal to 0 to x is equal to 2. Using some basic graphing strategies, you should be able to justify that the graph of this function pretty much looks like this, almost like the right side of a bell curve. So what we have here is we want to go from x is equal to 0 to x is equal to 2. So let's assume that this is equal to 2, just for the sake of drawing. So let's put 1 there, and let's assume that we want to approximate this with rectangles. It should be easily seen that left-hand rectangles will be an over approximation here, and 2 rectangles probably will be a little bit errorful, whatever that means. So I probably want a little bit more than 2 rectangles. Let's go with 4. So this is going to be equal to 0.5, and this is going to be 1.5, and then I'm going to have 4 rectangles. The first rectangle's left endpoint will be at 0, the second rectangle will be at 0.5, the third rectangle will be at 0.1, and the fourth and final rectangle will be based with the left endpoint generated from x is equal to 1.5. Right? So the area of these rectangles will be my approximation, which obviously is an over-approximation, which can be justified by proving that the function is decreasing on the interval 0 to 2. Right? So obviously what we've done is we've let n be equal to 4. Therefore, what is the length of each of these intervals? It should be trivial that it is equal to half, but you can verify it with the formula that we've proven or stated before, which is 2 minus 0 divided by 4, which is 2 divided by 4, which is equal to 0.5, which is what we have before. So therefore, the left-hand rectangle approximation with 4 subpartitions will be equal to 0.5 times f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. And using the function definition that I gave before, f of x is equal to e to the minus 1/2 x squared, and making sure you have parentheses when you're using your calculator, you can find that that's going to be approximately equal to 1.4068. Is this the exact answer? Of course not. It's just an approximation. So how can we make our approximation better? Just do more rectangles. Now let's assume that n is equal to 8. What is my delta x? Well, my delta x will be equal to 2 minus 0 divided by 8, which one can find to be equal to a quarter. So what is going to be my approximation? So A8L is going to be equal to our length for each of our rectangles times f of 0 plus f of 0.25 plus f of 0.5 plus f of 0.75, and this is going to continue all the way up to f of 1.75 as the last, and one should be able to verify that this is approximately equal to 1.30296. Is this the exact answer? Of course not. So how do we make this approximation even better? Obviously make n as large as possible. So obviously, the theoretical way to make this as exact as possible is to take the limit as n goes to infinity. One can verify with some fancy algebra that the limit as n goes to infinity of a and l will be approximately equal to 1.1963, with some decimals after it. If we take this as axiomatic, you can clearly see that as n gets bigger and bigger, the values get closer and closer. And we can also see that the values of A4L and A8L are also larger than the exact value. So, left endpoint rectangles give us what we want. Are they the best? Probably not. And as previously mentioned before, instead of left endpoint rectangles, you could also do right endpoint rectangles as well. So right endpoint rectangles are also a good alternative to left endpoint rectangles if for some reason you don't like the left ones. So how would you evaluate area approximations? With right. So obviously we're going to assume that the lengths of each of those rectangles are the same. So let's assume that that's equal to delta x. Now instead of starting at the left, we're going to start at the right of the first, which is going to be located at a plus delta x. And then the next is going to be a plus 2 delta x plus f of a plus 3 delta x, all the way down to the right of the last point, which is technically f of b, but you should also note that that's the same as a plus n delta x. But at least conceptually, know that that's the same as f of b. So, once we have this in expanded form, we should be able to quickly represent this in summation notation and write this as a and r is equal to delta x multiplied by the sum from k is equal to 1 to m, because notice that we have 1, 2, 3 down to n, so that changes the sum a little bit, of the same exact functional expression, a plus k delta x. So in terms of the differences between these summation notations, the only difference between left and right is left starts at 1 and ends at m minus 1, right starts at 1 and ends at m. And you can try for the previous example to look at the right endpoint rectangles for n is equal to 4 and 8 and compare to the exact value that was stated above. From our construction of left endpoint and right endpoint rectangle approximations, it's inherent that these both will likely have error, although it's possible that they could be exact, but probably only by chance or some very special, nice behaved functions like constant functions, which, you can always approximate smooth functions with constants, but usually they're not constant alone. So let's see if we can talk about the error that each of these approximations inherently have. So let's define the error for our left endpoint rectangles with n subpartitions to be equal to our area approximation minus the exact area that we don't know. And let's also define E and R to be equal to A and R minus the exact area. So there's a theorem, which I won't prove here because it requires a little bit more analytical tools than we have up to this point. But generally speaking, it's not super hard to prove. And let's suppose that our function is differentiable, and let's assume that the derivative is bounded above by m1 on this interval of interest AB. Then you can actually find upper bounds for these errors for both left and right. So for our left endpoint rectangles, one can show that the error is always going to be less than or equal to m1 divided by m times b minus a squared, and also the error bound on right is always less than or equal to m1 over m times b minus a squared. Right? So what exactly do we have here? So as n gets close to infinity, what do we have? As n goes to infinity, we have that epsilon nl and also epsilon nr, both of them go to 0, which means as n gets close to infinity, as we increase the number of rectangles, the error gets smaller and smaller and smaller, and eventually gets closer to the exact area that we're looking for. But if the length of that interval that we're trying to approximate the integral over is large, it still is going to go to 0, but not as fast. Also, in order for us to use this error bound, we also need an upper bound on the derivative. So let's go back to our example that we had before, where our function was e to the minus 1/2 x squared. So using the chain rule, you should be able to verify that the derivative with respect to x is just going to be equal to minus x times e to the minus 1/2 x squared. Let's look at the graph of what this looks like. So the derivative of this interesting little bell-shaped kind of curve is going to be looking like this, where x is equal to, or y is equal to 0 is a horizontal asymptote with the origin being an x-intercept. So we have this type of pattern. Also, using some other graphical analysis tools, you should be able to verify that 1 and minus 1 are always above and below this curve. Right? So, based upon this graphical analysis, we can observe that 1 is an upper bound. It's an upper bound for our function f prime of x. Keep in mind, this theorem only says that m1 is an upper bound, not a particular upper bound, because obviously if 1 is an upper bound, based upon this graph, there's probably another one slightly less than 1, and if you want to be extremely accurate, you probably want to choose the least upper bound. Using some calculus tools, that occurs when the derivative has a maximum. So you can take the derivative of the derivative, set it equal to 0, find those extreme points for the derivative, and locate the point for which it's concave down, because the other one is going to have a concave up behavior. So one can show that the least upper bound, which some people abbreviate by LUB, of this particular function f prime of x is exactly equal to 1 divided by the square root of e, which is approximately equal to 0.60653. Right? So generally speaking, finding the least upper bound can be a little difficult. So generally speaking, all you need to do to have an upper bound on your integral approximation is to just have any upper bound. The smaller the better though. So let's just take m1 to be equal to 1. So let's take m1 to be equal to 1, or if you know the least upper bound, take m1 to be 1 over the square root of e. So we already know that our 4-rectangle left-hand approximation is approximately equal to 1.4068. If we do not know the actual area, we need to answer the question, how accurate is this? Because we don't know, at least generally speaking, what this true area is. So from this theorem, the area approximation for 4 rectangles for a left-endpoint rectangle is going to be less than or equal to, again, m1 over m times b minus a the quantity squared, We're choosing m1 to be equal to 1, and our n is equal to 4, b is 2, a is 0, and we get this. So we have that this is going to be equal to 4 divided by 4, which is equal to 1, right? Yes, our error is less than or equal to 1. We can do a lot better by making our m1 a little bit smaller, 1 over square root of e at most. But from this particular thing, what can we say? So that means the distance from our approximation 1.4068 and the actual area we're aiming is less than or equal to 1, which means that the exact area is going to belong to the interval 0.4068 to 2.4068. So the exact answer is somewhere between 0.4 and 2.4. And that much we can guarantee just from this approximation. So we have our left endpoint rectangle approximations and our right endpoint rectangle approximations and error bounds for both of those approximations. And it's very easy to see that both the limit of left and right as n goes to infinity are both equal to 0. But just because the limit goes to 0 doesn't mean that the convergence rate is fast. We might need 5 billion rectangles just in order to get our integral to have an error bound of, say, 1, or whatever error bound that you desire for accuracy. So, is it possible that we can do even better with different approximations that don't require as many rectangles for that same accuracy? Let's look at a picture. So let's look at our little rectangle approximation. Let's just do one interval, one rectangle. So this right here is our over approximation, in particular A1L. And then here in purple, that is our A1R. Can we do better than this, even with just one rectangle? The answer is, of course, yes. Can you draw a simple shape that can easily do this? If so, what you can do is, again, let's go from A to B. And what we're going to do is we're going to go to that height and go to that height and connect them. And then we're going to find the area underneath that shape. In this particular picture, it is an under approximation, but it's not as much as an under approximation as A1R is. Because in this same picture, notice that all of this area here is accounted for, which is really great, but there's still a little bit of area that is missing. So what shape do you see here? That is a trapezoid. So if we look at this particular picture, for this particular one rectangle approximation, what do we have? So A1L will be equal to f of A times delta x, and A1R will be equal to f of B times f of x. So if we look at 1/2 AL1 plus AR1 times delta x, for example, then what we have here is the area of a trapezoid. So area of a trapezoid. Actually, there's no delta x here, and it's not obvious that that is the case. Let's show a little bit of work here. So if we take the red and we take the purple, add them and divide by 2, so we're just averaging the two values. So let's just write it. Some people aren't comfortable with that notation. So if we average the left and the right, what will we get? So that's obviously going to be equal to 1/2 of f of a delta x plus f of b delta x in this guys. Delta x can be factored out, so we're going to have 1/2 of f of a plus f of b times delta x. If you remember the formula for area of a trapezoid, it's 1/2 b1 plus b2 times the height. It's just sitting on its side, right? So this is b1, this is b2, and this is our height, and that's just the area of a trapezoid. So we've derived the area of a trapezoid formula. So let's just give this a name. This is called the trapezoidal approximation. So the trapezoidal approximation. So we're going to abbreviate this by ANT, T for trapezoid, which is going to be the average of A and L plus A and R. So is the trapezoidal approximations better than left and right? At least from that picture, it appears to be the case. But let's look at a theorem that gives us the error bound for trapezoidal rules. So let's suppose that the second derivative of the function is bounded above by m2 on the interval a, b. Then the error bound for trapezoidal approximations will be less than or equal to m2 over 12n squared times b minus a cubed. So if we look at this particular approximation, notice that yes, as n goes to infinity, epsilon nt will go to 0, but it goes to 0 in a quadratic speed, right? Which is a lot faster than the linear speed for left and right rectangular approximations. So trapezoidal approximations will get there a lot faster, generally speaking. So let's look at our previous example to sort of see how these numbers work out and sort of see how much better our trapezoids will give us over the left and right. So our function before, again, was e to the minus 1/2 x squared, and then f prime of x, which is equal to minus x times e to the minus 1/2 x squared, and f double prime of x, one can find to be equal to x squared minus 1, so inflection points at plus or minus 1, e to the minus 1/2 x squared. So one can find that the max of the derivative of f prime occurs at x is equal to 1 over the square root of e, and one can show that the max of f double prime occurs when x is equal to 2 times e to the 3/2, right? So again, those are going to be your least upper bounds for f prime and f double prime. If you know them, you can choose them to be your m1 and m2. But keep in mind, 2 over e to the 3/2 is less than 1 over the square root of e. So we can still choose m1 as to be equal to 1, and also m2 to be equal to 1 as well. You could choose 0.5, I guess, but those numbers are a little bit more complicated to work with if you just want to use paper. But if you're in a computer, you have nothing to lose by choosing the least upper bound. Right, and we chose 1 for our least upper bound for left and right, so it's a fair approximation to use m1 to be equal to 1 at least. So what are we going to get? So AL4 came out to be approximately equal to 1.4068, and AR4 will be approximately equal to 0.9745. So therefore, A4T will be the average of these two of 1.91907. So our question then becomes, how accurate is this? So how accurate is this? So what we're going to do is we're going to be taking m2 to be equal to 1 because it's an upper bound, but you can choose 2 divided by e to the 3/2 if you really want to. But if we choose 1 to keep simplicity, then E4t will be less than or equal to 1 divided by 12 of 4 squared, because we have 4 rectangles, and then 2 minus 0 cubed. And again, that 1 on the top is your m2, not your m1. And we can find this is approximately equal to 0.0416 something, right? So if that is the case, and we compare the actual area to 1.1963, notice how close we have for this accuracy. So we're guaranteed that the area is less than 5% in terms of decimal values from the exact area. So if we say that that's 0.04, that means the actual area is between, let's say, 1.19 minus 0.04 and 1.19 plus 0.04. So we're guaranteed that the area belongs to the interval 1.15 to 1.23, which indeed it does, right? So we're pretty much there, and this interval is so much more smaller than the original formulas were, right? So that's really great. So there's another approximation that we could use, and that's what we call midpoint rectangles. So midpoint rectangles. Midpoint rectangles. So we're back to rectangles again. You're like, oh, I was liking trapezoids. So what does midpoint rectangles looks like? So let's assume this is our function. This is our interval. Let's assume that we break it up into 4 pieces. So what we're going to do is we're going to grab the midpoint of each of these intervals and send that up, and that's going to dictate the height of our rectangles on those intervals. So this is going to be rectangle 1, this is going to be rectangle 2, this is going to be rectangle 3, and this is going to be rectangle 4, and this blue shaded region will be our area approximation. At least from my graph for this function, it doesn't appear too bad. So how exactly are we going to find this, at least in formula form? So notice that it's practically the same as left, except we're shifted to the right, a delta x over 2 term, or it's from the right and shifted to the left. So let's just do from the left derivation because that's pretty easy. So the midpoint approximation with n endpoint rectangles will be equal to delta x of the sum from k is equal to 0 to m minus 1, so we're basing it based on the left. And then we're going to have f of a plus, we can do, let's do k delta x plus delta x over 2. 2k delta x plus delta x over 2. Right? So once we have this, we can actually factor out some delta x here. So we can write this as delta x times the sum from k is equal to 0 to m minus 1 of f of a plus delta x times 2k plus 1/2. All right, so that gives us the formula for the midpoint rectangles. So if we think about this from the same exact example that we have, for example, in particular f of x is equal to e to the minus 1/2 x squared with 4 decimal points, 0 to 2, 1 there, 0 0.5, 0. Or 1.5 actually. Our midpoints are going to be located at 0 0.25, 0 0.75, 1.25, and 1.75. So those are the points that are going to be projecting to the heights for our particular curve. So that means A for M will be equal to 0 0.5 because that's still the length of each of our rectangles, which is generated from different points. And that's going to be f of 0 0.25 plus f of 0 0.75 plus f of 1.25 plus f of 1.75. And one can find for this particular function is approximately equal to 1.19909. And if you remember the exact values for that, that's pretty close, right? So what is the bound for this particular approximation? So let's suppose that the second derivative, f double prime of x, again, is less than or equal to 0 on the same exact interval x is equal to ab. So if we chose 1 for our trapezoidal approximation, you can use 1 here. Then the error bound for midpoint rectangles will be less than or equal to m2 divided by 24n squared, so it's still going to decrease quadratically, times b minus a cubed. But if you sort of compare this to the trapezoidal approximation, it's practically the same, but it's a half of the error bound of a trapezoid. So if you have 8 trapezoids, you in some sense only need 4 midpoint rectangle approximations to get practically the same exact amount of error. So therefore we can say that ANM is twice as good. It's twice as good as ANT. That's pretty great, right? And that's the midpoint approximations compared to trapezoids. So up to this point, we have 3 rectangle approximations, 1 trapezoidal approximation, which is in some sense the average of 2 rectangles, and they all have error bounds, which is actually pretty nice, with left and right rectangles being linear convergence, and trapezoidal and midpoint rectangles being quadratic convergence. So the next question becomes, well, can we do better than that? Of course, the answer is yes. But let's just make one little observation. The boundaries on A and L, A and R, A and T, and A and M are all linear boundaries. So what do I mean by linear boundaries? So if you think, for example, left rectangles, which is that, notice that that upper boundary is a constant function. If we look at, for example, right endpoint rectangles, the upper boundary also a constant function. If we look at midpoint rectangles, the boundary also is a constant function, which is a special case of linear. And if we look at trapezoidal approximations, the boundary again is linear. Right? So these are three constant linear functions, and this is not necessarily a constant linear function, but in this particular graph, it's a decreasing linear function. So how can we approximate the boundary of the curve better than a linear function? And you're like, okay, well, polynomials are pretty nice. These are technically degree 0 polynomials. Left endpoint, right endpoint, midpoint rectangles. They're all degree 0 polynomial approximation boundaries. And this is just a degree 1, right? So degree 0 boundary, degree 0 boundary, and degree 1 with our trapezoid. So what's higher than degree 0 and degree 1? That would be a degree 2 boundary, right? So if we want to do better than linear boundaries, we can do parabolic or quadratic boundaries, right? So one of the more famous area approximations that use parabolic boundaries is known as Simpson's approximation. So Simpson's approximation. There are several others, but Simpson's probably is the more famous of them all. So the Simpson's approximation, which I'm going to abbreviate as ANS, so it's going to use n parabolas, can be proven to be equal to 1/3 of a weighted average of the midpoint and trapezoid, weighing the midpoint a little bit more heavily. Because the trapezoid definitely accounts for a lot of the change of the curves, but midpoint is definitely just better. So what we do is we weight the midpoint approximation a little bit more than the trapezoidal approximation. So it's just a weighted average of the two, right? So this is our Simpson's approximation, which approximates the boundaries of our curves with parabolas. So for example, if we have the sine function, which sort of looks like that, if we sort of look at this particular curve, this is probably a horrible sine graph. Let's assume that's true. Approximating the boundary of sine on some particular function looks so much more better compared to, say, two lines where it looks sort of like a triangle. So parabolas naturally fit curves a lot better than linear curves. And that's sort of what motivates Simpson's approximation. Whereas the proof that this is indeed a parabolic approximation, that might not be as intuitive, but maybe later we'll get into the proof of that. So now one can ask, how accurate is this? So let's state the theorem for that. So now let us assume that the fourth derivative is bounded above by some number m4 on the interval AB of interest. Then the error on Simpson's approximation will be less than or equal to m4, our upper bound, 180, some magical number, n to the fourth times b minus a to the power of 5. So what do we have? We have that left and right converge at a linear rate, midpoint and trapezoid converge at a quadratic rate. We're sort of skipping cubic convergence right here because we're just jumping to n is equal to order 4. But what we have here is a quartic convergence rate or degree 4 convergence rate. So it's very easy to see that Simpson's approximations converge so much quicker than trapezoid, midpoint, left, and right. And it just requires us to have an upper bound on the fourth derivative, which hopefully isn't too hard. But if it is analytically difficult, you can always use forward, central, or backward difference approximations for the fourth derivative if you really need one. So Those are some of the most famous and useful approximation tools for approximating areas under curves, which are sometimes called as definite integrals of functions. There are several others and so much more to be said about finding areas under curves with functions, but we'll get to that at a later time. Hope you enjoyed this video, and I'll see you then. Take care.